students, good morning all of you. Today in our lecture, I need to explain the magnetic field at an axis of a circular current carrying coil. In our previous session, we were discussed biotsavartlaw and in that we have to find the magnetic field of a finite straight current carrying conductor, and due to that we have to clear our doubts, so many of our doubts along with the infinite straight wire and semi-finite straight wire and semi-infinite straight wire. Okay, and one more we have to discuss. According to the biotsavartlaw, the magnetic field at the center of the current carrying circular coil. Okay, due to that we have to discuss for the semicircular coil and quadrant coil and also an arc. So these are very well discussed in our video, in our channel. I have to provide in our iCards. You have to check once. Okay. So now let us start our topic. Before going to that, you have to subscribe my channel and share to your friends and like and comment. Okay. So let us start our topic. Magnetic field at an axis of a circular current coil, current carrying coil, right? So very important. So this is the one of the imaginary part we have to learn here. Okay, so let us start. So here there is a circular current carrying coil. So this is the circular current carrying coil. Circular current carrying coil. So having the current here, that is I. From the center point, the radius of the coil it is A. Okay. At the axis, on the axis of a coil, so this is the axial line, axis of a coil. From the point O to x distance, there is a point P. There is a point P. So now we have to find at point P what is the magnetic field acting. What is the magnetic field acting by the circular current carrying coil. Circular current carrying coil. That is our aim. Okay. Right. So here we have to assume there is a smallest element dl here, and here the smallest element, here the smallest element, and here the smallest element dl here. Okay, so this is the smallest element dl. From this point we have to join a line which to the point P, and one more line we have to join, so the smallest element P. So here the angle made by this, it is theta, and this is theta. Okay. So now we have to find the dP value according to the biotsavartlaw. So here there is a current carrying wire, and we have to assume the smallest element dl. From this arc, at the distance of r, there is a point P. So here the distance, here this distance is not equal to this one, right? So this is the distance from the axial line of the axial point, which you have to assume P point. But the distance it is from dl to point P. So this is the distance we have to take in here. So this r is equal to this one. So here the angle made by the angle between, here the angle between it is theta. So here where we have to take in the angle, here this is the direction of the dl, and here the theta will be taken, that is 90 degrees. Clear? Okay, let us check once. So here this is a circular current coil, current carrying coil. This is the circular current carrying coil. Okay. So here we have to take here in this way. So this is the coil. This is a circular current carrying coil. Right? So this is the axial line. So this is the axial. the axial line passing. This is the axial line which we have to guessing a point, that is P from the origin to x distance. Okay, and here there is a DL element. So here in this way, so this is the DL element. The current is I passing through along with the circle. Okay, so here there is the DL element, right? DL element. So this is the R here. This is the R. The angle between these two is, so whatever we have to changes, it is 90 degrees. It is 90 degrees. Clear? So this is the 90 degrees. Similarly at this point, this is also having the 90 degrees. So here the current, it is DL. So at this point here, this is the current here. At this point there is an angle, it is 90 degrees. So whatever the DL element we have to choose in here, that has the 90 degrees. Okay, so this is the circular current carrying coil. Okay, right. So now we have to find that the dB value, the magnetic field dB. So from the biotsavartlaw, where dP it is equal mu0 upon 4 pi ideal sin theta by r square here, where theta is equal 90 degrees, dB is equal mu0 upon 4 pi ideal by r square here. So this is the equation 1 you have to take, since theta is equal 90 degrees. Since theta is equal 90 degrees here. So here the dB is divided into two components. dB is divided into two components. One is the horizontal and another it is the vertical component. So the horizontal component, so this is a circular current carrying wire. Okay, so this is the horizontal, right? This is the horizontal and this is the vertical. This is the vertical which is perpendicular. This is the horizontal in this way, right? So this is the horizontal. Horizontally it is dB cos theta, right? And vertically it is dB sin theta. This is vertically. So let us see here. So this is horizontally. So this is the horizontally dB cos theta and vertically dB sin theta here. And similarly, according to this DL element, horizontally there is a dB cos theta, and vertically it is dB sin theta. So these two are in the same line, but you have to, I want to focus, then just I have to be taken as a small variation. Actually they are in same line, right? So from this, the dB cos theta and dB cos theta are opposite to each other. They can be cancelled out. The net magnetic field is dB sin theta. And 1 dB sin theta for this DL element, another dB sin theta for this DL element, one more DL element, there is a dB sin theta, one more element. So how many DL elements we have to take? That types of dB sin thetas are there. That's why you have to take in the net magnetic field. The net magnetic field is equal, B net is equal integral of dB sin theta throughout the circle. Circle integral of dB sin theta. Clear? So where dB is already defined by us, that is mu0 by 4 pi ideal by r square. Where r it is nothing but here. So this r can be find out by us, that is r it is nothing but, how we can find that? side square plus side square. This is the hypotenuse where it is a square plus x square. So here r it is equal a square plus x square under root, that is 1 by 2 here. Clear? And simply you have to substitute here, that is circle integral of dv nothing but mu naught by 4 pi I dl by r square into where it is sin theta. This was the sin theta. So how we can integrate here? There is no d theta value. So let us find the sin theta from any triangle here. Any triangle. This one or this one. So sin theta is equal opposite by hypotenuse. It is a by r here. A by r. Right? Let us write the sin theta value here. Circle integral of mu naught upon 4 pi I dl by r square a by r. It is r square into r. It is r square into r. It is a cube, r cube. That is mu upon 4 pi I by ia by what is that? R cube integral of dl. So we have to integrate the dl value. So integral dl, it is nothing but circumference of the circle. So that is dl, it is equal, you can write that. Okay. So dl, it is equal mu naught upon 4 pi I a by r cube into what is that? Integral dl, circle integral dl, it is equal capital L. The del should be circumference of the circle, that is 2 pi a. 2 pi a. 2 pi r replacing by the radius, it is the a here. 2 pi a. So let us simplify. A into a square. It is mu naught by 4 pi I can write that pi, it is 2 into I. So let us write here 2 I pi a into a square by what is that? R cube. So this is the r value, a square plus x square whole power 1 by 2. It is a square plus x square whole power 1 by 2. It is cube, that is 3 by 2. That is 3 by 2. Okay, r cube, it is equal a square plus x square whole power 3 by 2. Okay, so this is the dB. So let us simplify here. How we can simplify that was, so I want to remove this one. So therefore dB is equal, so dB, sorry, it is the total B net is equal, where B net is equal B net mu naught upon 4 pi, right? That is 2 pi a square into I by a square plus x square whole power 3 by 2. Okay, where pi into radius square. So pi a square, it is equal area of the circle. Area of the circle. Let us write that. So it is equal to mu naught upon 4 pi 2 into I a by a square plus x square whole power 3 by 2. So here let there are n number of circular current carrying coils are there. If there are n number of circular current carrying coils are there, then the net magnetic field was NIA. N into IA. So n it is the number of coils in a circular scheme, right? So where n it is the number of coils. So NIA, here the NIA, it is denoted by the one special word, that was the magnetic dipole moment. Magnetic dipole moment. I will be explaining this one in our next session. Magnetic dipole moment. So this is the NIA. NIA. Right? This is capital M. M is equal to NIA. So hence we can write that B net is equal to mu naught by 4 pi. It is 2m by a square plus x square whole power 3 by 2. So this is the net magnetic field at an axis of a circular current carrying coil. So B net is equal to mu naught upon 4 pi 2m by a square plus x square 3 by 2. Right? So this is seems to like BA. So this is the B net, where you have to write that mu naught upon 4 pi. It is 2m by a square plus x square whole power 3 by 2. So this is the net magnetic field at the axis of a circular current carrying coil. So this maybe looks like say the magnetic dipole moment at an axial line of a dipole, magnetic dipole, right? So here this is the magnetic field, so here, so magnetic field at an axis of a circular current carrying coil. So if you like this video, please share to your friends, and if you have any doubts, please comment in the comment section. Thank you.